This is a really important lesson, probably one you're going to want to watch more than once. Because in this lesson, we now consider what happens when substitution and elimination can compete with each other. And the reason that you're going to have to handle this is you will be given a number of problems on the exam, most likely, where you have to predict the products. And previously, when we were just considering substitution reactions, you only had to write a substitution product. And in many cases, you didn't even have to necessarily determine if the substitution went by the SN1 or SN2 mechanisms in order to be able to write a substitution product. However, if substitution and elimination are both possible products, you need to know when you have to be able to write elimination products as well. And furthermore, you'll need to know whether substitution or elimination will be the major pathway under a particular set of reaction conditions. So I would like to start by listing the factors that you need to consider when doing such an analysis. And I consider the factors in the following order. So the first three factors are the ones you're always going to have to consider. So the structure of the alkyl halide. Is it primary, secondary, or tertiary? And closely related to that, number two, is whether or not there is resonance stabilization. Because remember that a secondary with resonance is equivalent to a tertiary. Fundamentally, you're going to have to classify your starting material as to whether it can go through a carbocation mechanism, namely the SN1 or the E1 mechanism, or it cannot go through a carbocation mechanism and is therefore limited to the SN2 or E2 mechanisms. Once you figure that out, then you have to consider the base strength of your nucleophile/base. And the reason you need to consider that is you need to know whether it is a strong enough base for E1, as we saw in a previous lesson, or a strong enough base for E2. Then you've got to consider how good of a nucleophile you have if you're proposing a substitution product. In other words, if you are proposing an SN2 product, do you have a good enough nucleophile for SN2? Something we have also considered. Fifth thing you should think about, although it's not going to matter quite as much, is the polarity of the solvent. Remember, SN1 and E1 reactions that go through a carbocation are going to require a very polar solvent. SN2 and E2 reactions do not care so much. And then finally, if you have an unsymmetrical alkyl halide, in which case Zaitsev's rule will apply to elimination products, you have to consider the size of the base. Is it a small base or is it a large base? So looking at this list of factors, you will basically see most of the last set of lessons all coming together in one problem type. So now I'm going to give you the master table that tells you what happens under each of the most important set of conditions. And what I've done is I put alkyl halide structure as the row headings, and then base strength as the column headings. So the good news is in many of these situations, you do only get one product. So for example, if your alkyl halide is methyl, you will only get substitution only by the SN2 mechanism. Obviously, methyl cannot do SN1 because the carbocation would be too unstable, but it cannot do elimination because there are no beta hydrogens. In fact, there's not even a beta carbon. For primary, once again, if you're going to do substitution, that substitution will only go by the SN2 mechanism. Now, what I neglected to say a minute ago was in parentheses under SN2 only, I wrote assuming a good enough nucleophile. As always, if you're proposing a substitution product, you have to make sure that the nucleophile is good enough to undergo SN2 substitution. So in the primary case, If you have a very weak base or a moderate base, E1 is not going to be a possibility. So in both of those cases, you're just going to have SN2 substitution. If, however, you have a strong base, hydroxide or stronger, then you could have a mixture, or will have a mixture, of the SN2 substitution product and the E2 elimination product. But in this case, with primary, SN2 will be the major product. And the reason for that is primary is more sterically accessible for the nucleophile to come into the backside of the carbon containing the leaving group and do substitution. And also, if it is primary, there is only a maximum of 3 beta hydrogens if it is an ethyl bromide. Anything bigger than that, there will only be 2 beta hydrogens. So statistically speaking, there are not a lot of beta hydrogens for the base to go after, so it will preferentially do substitution. Okay, secondary, once again, you're not, under most situations, we will see an exception in several lessons, you will not get E1 elimination with a secondary. So given the opportunity, it's going to want to substitute by the SN2 mechanism, or if the base is strong enough, eliminate by the E2 mechanism. But in the cases of the very weak base or the moderate base, where E2 elimination is not going to happen, you will get SN2 substitution if the secondary alkyl halide is small. And if the alkyl halide is large, and think back to the lesson where we talked about the criteria for small secondaries, if the alkyl halide is too large of a secondary for SN2 substitution, you will actually get no reaction. Okay, but in the case where you do have a strong base, a strong enough base for E2 elimination, you will get a mixture of the SN2 substitution and the E2 elimination product, favoring the E2 elimination product if the base is small. Sorry, if the alkyl halide is small. If the alkyl halide is large, in which case it cannot undergo SN2, you will exclusively, in this case, get the E2 elimination product. Okay, the larger the alkyl halide, and the larger the base for that matter, the more likely you are to get elimination. The smaller the alkyl halide, the greater the amount of substitution product you'll get. Okay, now we move to tertiary. And when I'm in the row for tertiary, I wrote tertiary or resonance stabilized, because resonance stabilized secondaries, or even in some special cases like benzylic, resonance stabilized primaries will react like tertiaries in that they can go through carbocation mechanisms. So with a very weak base, weaker than water, Cl minus, Br minus, you will get exclusively SN1 substitution, because we don't even have a base that's strong enough for E1 elimination. With a moderate base, one that is strong enough for E1, you will get a mixture of SN1 substitution and E1 elimination. I normally write that you'll get approximately equal amounts of the substitution and elimination products. That will vary a little bit from specific molecule to specific molecule, but as a rule of thumb, you can say that you have equal amounts here. When you have a strong base, one that is capable of doing E2 elimination, in this case, I am essentially going to say that you will exclusively get the elimination products. Realistically, you may get a tiny amount of SN1 substitution product, but think about it this way. Elimination can go by either the E1 or the E2 mechanism, and in order for substitution to take place, you are committed to going through the carbocation mechanism. And then furthermore, if you have a tertiary, there are going to be a lot more beta hydrogens for the base to pluck off and do elimination. So statistically speaking, it is much more likely that you're going to get an elimination product. So in this case, 2 elimination mechanisms, steric hindrance as far as substitution is concerned, and a large number of beta hydrogens. You are safe if you just write elimination products if you are in this box of a tertiary and a strong base. Okay, one last note on this topic is that E1 and E2 will give the same products. When we were talking about substitution, you had to decide if it was SN1 or SN2 to give the product in the case of a chiral alkyl halide, because you had to know if you were going to draw just one enantiomer or a racemic mixture of enantiomers. It doesn't actually matter if it's going to undergo E1 or E2. If it's going to undergo elimination, it's going to undergo elimination, and you will get the same products. However, when different elimination products are possible, the rule that you have to use to determine which elimination product will be the major product is Zaitsev's rule. So you have to look at the size of the base. That's why that's factor number 6 at the top of this. If it's a big base, you'll get the anti-Zaitsev product. If it's a small base, you'll get the Zaitsev product. So it doesn't matter if it goes E1 or E2. What matters is the size of the base and whether you're going to get the Zaitsev or the anti-Zaitsev product. Okay, so that brings us to the end of our culmination of our discussion of elimination reactions of alkyl halides. This is a topic that's going to need a lot of practice, so you're going to have to look at a lot of different practice problems and decide if they're going to substitute or eliminate. But moving forward in presenting the material, we are next going to move into elimination reactions where the starting material is an alcohol instead of an alkyl halide.